Well, looks like we can start. Welcome back, folks. We're now into week 5. The exciting thing about that number is it's a 16-week semester, but week 16 is just finals week. So after this week is over, we're 1/3 away through the entire instructional weeks of that course. And we're in really great position to really start moving through the derivatives. We're going to be working into the derivative as a function, section 3.2. We mentioned pretty much what we're doing in 3.2 is not anything too different from 3.1. We're just extending on some of the ideas we saw there, focusing on the graph. Yeah, I agree. Being already a third done is really kind of a breakneck pace sometimes it feels like. Before we know it, we're going to be, say, in chapter 4, chapter 5, just about finishing off the course around week 12 and so on. But for what we're going to be doing today, it's more of the same, looking into the graph of the derivative, focusing on it as now a brand new function that's derived from the original function, y equals f of x. And if we have time, we're possibly going to start section 3.3 as well. 3.3 is where we start looking into the other ideas to compute the derivative in a more fast, efficient way, where we don't have to always cite the limit definition from scratch each and every time. And so that's going to be the differentiation formulas in this section here we'll be investigating. Also, since these are algebraic topics that we're going to be running into quite a bit in section 3.3, I posted both the actual formulas and worksheets to go along with them for both exponent laws and logarithms at the same time. Logarithms are posted a little bit early. We're going to need this information when we're in the very last section of chapter 3. But I saw no harm in just posting it early, so it's available. Well, we got through exam 1, so congratulations, folks, on getting through it. The average was quite high, and there was 3 perfect scores in the entire class, so congratulations. Any questions at all, folks, before we start today's work? Okay, probably the big question is, what exactly is a derivative? It takes a lot of work to really say, because you have to know knowledge about limits, use tools with continuity to say what it is and to actually compute the thing from scratch. And that's what the review here on unit 3.1, or excuse me, section 3.1 was all about. We start by thinking of a slope of a tangent line. If we have original function y equals f of x, that's this curvy one that goes through. To calculate the slope of the tangent line, the one in blue right here, we had to take a particular limit. It's this one. But the thought was, you can take the slope using 2 points like this, label the points as x1, x2, y1, y2, find the slope of that secant line, and as that point gets closer and closer in the limiting value, when it hits this spot, we have the slope of the tangent line that we wanted when this limit exists. And here's what it looks like. If we plug all this information in from the original slope formula, we're taking the limit of f of a plus h minus f of a divided by a plus h minus a rather, and it just simplifies down into that limit. So this was the big idea of why we needed limits in the first place. But the major reason to think about this starting point is just to review how we got here, but also to start focusing on what m is. That's the derivative of the function at the point a for x. Any questions at all, folks, with just the refresher here? Okay, we calculated a couple derivatives when we were in these notes, but when we moved over to section 3.2, the same exact formula is back. Instead of calling it a slope, we emphasized we're now talking about the derivative of f at a value x. So instead of having, say, a number a here, whether it's an actual number like 1, 2, 3, or just undefined, say, a itself, we're switching to x. And so we put an x here and an x here. But it's the same exact definition either way we look at it. And it's still equal to the slope of the tangent line in this same format right here. We use this knowledge along with this increasing-decreasing theorem to take a function like this one and sketch the derivative down below. And it's tricky enough that we spent a good amount of time doing this when we went on to the weekend last class. I will focus on doing this from scratch again on a brand new problem to start us out today. But here's a refresher and the big takeaway on this. If you find out where the function is decreasing, that means the slope of the tangent line is negative, but the derivative is the slope of the tangent line. So when we were going down below its derivative, it had to be negative. But it's increasing until it hits 0 right here. And that's because at this point, the slope of the tangent line is exactly 0 for a horizontal tangent line. And so that 0 value, put a 0 on the graph. Then any tangent line you put on here, it's going to have a positive slope. So we were above the x-axis until we leveled off again. We got a local maximum, horizontal tangent line. And so the derivative in green, y equals f prime of x, had another 0. And that's that same kind of process. Decreasing means the derivative is below the x-axis. Increasing means the derivative is above the x-axis. Any questions, folks, with this review topic here before we look at another situation? Okay, so the big challenge is, what is the derivative? How do you define it? How do you compute it? And how do you plot it conceptually, just based on a curve like this? Another big challenge with the derivative is connecting it to an application. That could be a good amount of work just in and of itself. And so that's what the next example 2 is all about. But also there's some brand new notation that we have to kind of digest and take a look into as well. The derivatives are an interesting topic in the sense that there's a lot of different ways to indicate the same thing. F prime of x is the derivative of f at x, but occasionally we use this symbol here. If you just use an ordinary y prime, you're still talking about the derivative. We just switched out from emphasizing it algebraically, the y value, versus the function notation, so no big change there. And these notations are kind of nice because they're just really fast. You put f with a prime on it, now you're talking about the derivative. That notation, in fact, even has a name. This is called Newton's prime notation, or one of the people who derived, defined, or discovered, however you'd like to say it, calculus. So Isaac Newton gets named for this notation. But another thing that happened way back in the day, quite a few years ago, was calculus was also independently discovered by another individual, Leibniz in Germany. These people, they didn't know each other. They both happened to come upon these ideas around the same exact time, and they eventually did connect. But it's interesting to know the other people credited to deriving or discovering the entire landscape of calculus is Leibniz. And did I spell that right? No. Let me try again. Sorry, I don't speak German. Let me try one more time. Leibniz. And this is Leibniz's notation. Leibniz notation feels kind of clunky. We have a dy over a dx. Or if you're emphasizing the function f, you could call it a df over dx. Or you can think of this as an operator, d over dx, acting on f to differentiate f. But all of this information here is still saying the same exact thing, the derivative of f at x. Other courses might use these other ways to indicate the derivative. Mentioning it here just for the sake of completeness, we're going to focus mostly on these right here. So dy over dx is the derivative of y equals f at x with respect to x. Is another way to say this entire construction right here. Even though it looks really clunky, it's actually super useful, especially if you're dealing with some kind of applied situation, say like in this case. We have a graph of the population of P of T, the number of yeast cells in a laboratory culture during an amount of time T hours after the experiment began. And when we look at dP dt, this entire thing is just saying the derivative of P, the population, with respect to, well, that's P in the numerator, the population, but it'll be respect to the new variable, this time T for time. So with respect to time. So it's kind of clunky, but we'll see really a good reasons why this is very useful as we go through the course and do more and more applied problems. So far, this is the entire graph. The number of E cells starts off some positive value. So we actually put a culture inside of a Petri dish. We allow it to incubate to around 15 hours. This is about where the graph ends, or just a little bit after, it looks like. And this is pretty much a typical curve that might model the population. Possibly what they did was measure the population size every 10 minutes or maybe 15 minutes. And then they produced this smooth curve to model the population size. Notice it starts off increasing kind of slow at first, but then right around the 5-hour mark, this curve is steep. The population size is increasing rapidly, but only for so much time because there's limited resources, limited space inside this Petri dish where the yeast culture is. So eventually it reaches a maximum size and levels off right around here. So if we're going to graph the derivative dp dt, that's just the slope at any point on this graph. At some points, that slope is pretty high for the tangent line. At some points, it's pretty small, but it looks like it never exactly reaches zero, maybe pretty close to our eyes. It doesn't start off as a zero slope here. It looks like it starts off just ever so slightly. If we really zoom in on that, looks like it's always angled up. So the derivative is never zero on this graph. Let's go ahead and sketch another graph, just like we did on the example one of these notes, to match this situation. A real good idea is to try to make your axes be identical so we can match up the slope of a tangent line we might put down with the actual derivative we're about to plot. Let me use the same color, so just reminding myself, we're going to graph this one in green. So here's the next axis. I'm emphasizing quadrant 1 on this graph because it looks like the derivative never actually zeroes out. Probably gets really, really close here, but it never goes to negative. Everything is always increasing. So this is still at 5, 10, 15 hours. And now this is for the graph that's indicated this way. If this was P, the number of E cells, this time it's dp dt, the rate of change of the number of E cells, or just the derivative for short. dp dt. And just to emphasize both notations, if you called it P prime, you're talking about the same exact thing. That's just Newton's prime notation in that case. Okay, so let's see what's going on, moving left to right. So if we start off here, we should really zoom in on that to see what's going on. We start off right about here, pretty close to the starting position, and put down any tangent line. Maybe your tangent line is here. It will look about like that. With the understanding that if we zoomed in right in this spot, both this dashed green line and the red curve are going to look identical. It has a positive slope for sure. But if we moved more and more to, say, right around here, the line gets more and more flat. It's getting close to zero, but probably, again, never actually getting perfectly horizontal. So that would possibly mean that right at the zero mark, the derivative is non-negative. But that makes sense in the understanding that if that's the rate of change of the population, the derivative, how it's increasing with time, if we said zero, we would have meant the population is never increasing. That means the population size would stay constant for all time. But the fact that it's increasing always, getting a higher and higher population, means the derivative needs to start off on some non-negative value right over here. So that's our first tangent line. And notice also, if you're way over here, that's meant to be green again. If you're way over here, the tangent line probably looks almost perfectly horizontal. Maybe it actually does hit horizontal right around the 15-hour mark. It's hard to say with what they gave us on the graph, but that would mean if it did hit the horizontal, population stopped if we put a zero value there. We think it's still growing. Maybe it's just really close to zero. Let the point float above the x-axis. And if this was an exam question, I wouldn't be super critical about that. If your dot is just in the right ballpark, you would get full credit for this kind of graph. Let's look into this really carefully. Again, imagine this is an exam paper. You have a magnifying glass. I mean, maybe that's not appropriate for an exam. That'd be kind of weird. But it looks like it's possibly horizontal. Really hard to tell the resolution on this one. So if you kind of make it go like that, putting it close to the zero value or right on the zero value, I would say either answer would be just fine on this one. So it starts off growing slowly. We have a point just above the zero value on the x-axis, the t-axis for time. Then it levels off clear up here, so we're close to either right on the t-axis or just above. And now we're wondering what's happening in the middle. Here the slopes are pretty large. Until somewhere around here, it reaches its maximum because we have a slope going like this out here. Maybe that's a slope of about 1, for example. Out here, we have a slope for the tangent line going like this. But somewhere in the middle, it's even more steep than either one of those. Hard to say exactly where. Maybe it's the 5-hour mark, or maybe, say, 6 hours. But somewhere out here, there's a tangent line with the largest value of the slope whatsoever. Let's say it's that point right there, right at the 6-hour mark. If I drew this tangent line, this one's kind of weird because it's going to go like this. You see if I can draw it a little bit better. It will look about like that, going through the graph with the one spot below, one spot above. If we zoom in on this repeatedly, the curves are going to overlap, look almost identical. But that would tell us that somewhere out here, we have our maximum slope. I don't know exactly what it is, so I'm leaving the y-axis blank. This is just a qualitative sketch. But this is the point that's going to match up from here to here. This is the point at which the population is growing the fastest, but we can relate the population growth to just the slope of the tangent line. The slope of the tangent line is the derivative. And so if the population is growing the fastest at that point on the graph above, that means this is the largest. Value for P prime, the slope of the tangent line, which is the rate of change of the population growth with respect to time, or you could just call it dp dt for the same exact meaning. So this one is a more challenging graph to produce for sure on this one, but still thinking in terms of this is nothing but a derivative. It's the slope of the tangent line at any one spot, and we hit a maximum. It means our graph is probably going to look something along these lines. Hits a maximum, comes down, and starts to get closer and closer to zero, potentially hitting that zero. Looks like I kind of missed. Let me try again. But for a qualitative by hand sketch, I'm being kind of picky on how I put it down. I wouldn't be picky on how I graded these. This would be my graph for dp dt. What it's telling us is the population is always increasing, but some moments of time it's increasing the most, say around the 6-hour mark. Then around 10-hour mark, it starts to fall, still increasing, but the rate of change is getting smaller and smaller as we get closer and closer to 15 hours, possibly hitting zero but beyond. Well, that's plotting yet another derivative, but this time with context. Any questions at all, folks, getting that down on paper? Okay, once again, any sketch you're asked to produce like this, I won't ask you to state the values on the y-axis, because to really state those values, you need to come up with that slope. And sure, we might be able to visually estimate it through the graph. We're going to focus more on actually dealing with problems that we can do the graphs and the slopes in more exact ways that we'll see in these notes. But suppose, for the sake of argument, that we did have a value that dp dt equals 30 when we evaluate it at t equals 5 hours. So this is just like saying the derivative p prime is 30 at 5 hours. So that would be a synonymous for that notation. P prime at 5 hours is 30. So Leibniz notation, we would write out like this, dp over dt. This bar is called an evaluation bar. We're saying take the derivative, plug in 5 hours and evaluate it, and the output is 30. Or an ordinary prime and function notation, we're saying p prime at 5 comes out as 30. So if we can say exactly what that number means, we're doing the good work of putting a derivative in context and saying exactly what it would represent in this applied problem, looking at the population growth of yeast cultures. So we'll provide a practical interpretation, use the context, much like we did with a limit problem on an exam setting in a class in lecture notes. So the way this will go is you start writing out what these represent. P itself is the population of the yeast cells, so we can say the rate of change of the population of yeast cells with respect to time So that's just reading out what this is. It's the derivative, but we can call it the rate of change. But if we're going to say exactly what it is, notice the derivative, its value changes with time. So we have to mention the actual input. So let's say here, at 5 hours is 30. But if we're going to say what that means using the context, we have to put numbers to that, or excuse me, a unit to that is 30. And here's the great idea with this Leibniz notation. The units are kind of looking at us. We take the unit of the numerator, much like if we were dealing with a slope. P is the number of E cells, so say 30 E cells. Then we take the unit of the denominator per hour. So that's the rate of change. In other words, you could say, if you give a different kind of interpretation, the population is growing at a rate of 30 yeast cells per hour at time 5 hours would be an equally valid interpretation for this derivative. Now let's mention that just for a different take, but first, any questions so far with what we've written down? Yeah, that would work as well. We should also put in the units as well to finalize it so that we're really bringing in the context and saying what the 30 itself represents, because that's one of the trickier things about these derivatives. This isn't, say, the population size is 30. It's saying it's growing by the rate of 30 cells per hour. So yeah, that would work. Just make sure to include the unit in entirely. Other questions so far? Okay, once again, we used a big context of the derivative of thinking about speeds, velocities, for example. The derivative is like a speedometer on something, but if we change the concept to population, that kind of changes in a certain sense, but it still is a kind of speed in a certain sense. It's saying the growth rate of the population is 30 cells per hour when we're at the 5 hour mark. Let's say that's another equally valid way to represent that. Let's call this solution 2. I kind of like this interpretation better because if you tell people the rate of change of the population, now you have to tell them exactly what that means. So another way to say it is borrowing what Haley suggested at the 5-hour mark, the population is growing at a rate 30 cells per hour. Again, either way you say it, the major thing you have to convey is we're dealing with the slope when we're thinking about the derivative. So there'll be a unit for a numerator, a unit for a denominator, but that's what Leibniz notation is resolving for us. It's giving us those units right away in these kind of applied problems. But again, these are pretty challenging kind of concepts. We're mostly done with the notes already at this point, but any questions or comments so far? Okay. Other things that I have down here on the notes are ways to compute the derivative just a little bit faster, because you've noticed that the derivative is a pretty tough computation. And some of the problems, the algebra just absolutely kind of blows up on us. So we take tons and tons of algebraic steps just to do one derivative, get one slope. So it's a good idea to think in terms of what is the derivative geometrically in certain situations that can completely resolve what the derivative equals. So no matter what we are looking into, whether it's population of yeast cells or just a generic mathematical function, the derivative is just a slope. It's a slope of a tangent line at a point for an original sum curve. And so if your function is f of x equals 12, we can get the slope of that tangent line immediately. First, let's kind of think about this. Let's connect the dots with what the derivative is, the recitation here of the derivative, compare it against the original function. I want to match up the color coding. Let me fix that real quick. So here's the original function. If we put this on the graph, here's what it would look like. This function is kind of special. This is a constant function. What we mean by that is the input is irrelevant. No matter what value you've chosen for x, the output is always constantly equivalently equal to 12, no matter what. So if this is, say, 6, then 12, here's the graph of our function. And now if we were to say, find the slope of the tangent line at any one of these points, the constant function is kind of special, right? Any point you pick, say it's right here, the tangent line is going to be automatically horizontal because the original function is also horizontal. That means the derivative of f at x is 0 everywhere on this graph, no matter what. If we were to plot it down below like we did on the others, here's the graph of the derivative. It's kind of hard to plot because it's overlapping the x-axis. Let's blow up this pen a little bit. Here it is in bold. Y equals f prime at x. And so that's kind of an amazing sense, or amazing problem in a certain sense. Any constant function you pick up, graph is always horizontal flat. That means the tangent line is also horizontal, but the derivative is always equal to the slope of the tangent line. So in these cases, it's always 0 no matter what. Any questions at all, folks, with part A? Okay, here's what makes part A massively tricky. Your constant functions can be super, super disguised sometimes. If it's just 12, it's a little bit more overt. That's a constant. That's just the number 12, right? But if your function was, say, f of x equals the square root of 13, it looks more abstract. It's still just a constant function, f prime of x equals 0. But it gets worse. What if it was this, f of x equals natural log of 12, something random like that? Now it starts to look like something more built up, like an honest function. But it's the same sort of situation. Here's natural log 12. Where did it go? Hang on, forgot to plot it as a bona fide function. F of x equals the natural log of 12. And there it is, just another completely flat curve. It looks like it's more special because it just feels abstract as a constant. The natural log 12 is just the number 2.48 and some change, it's irrational. So the derivative in this case is still zero. So this kind of begs the question at this point, what makes a function constant? It's the absence of the input variable on the right-hand side. If we're talking about natural log 12, the moment you put in the input variable x, now it's no longer constant. It's going to change on you. The slope is different at every single point of the tangent line. And similarly for all these other problems down below. So the moment you spot there's no x there, it's constant. And the derivative is immediately zero. Even if we plugged it into this entire tangent line equation right here, excuse me, the derivative equation right here for the slope, we would still get zero because f of x plus h for this first problem is 12 minus f of x is just 12 again. You're just taking 12 minus 12, getting zero in the limit. So that's our first amazing case where we don't have to actually use a limit definition. We can compute the derivative immediately the moment we spot a constant. And here's the next amazing case. This one's not a constant function, but it's the very next best thing. This is we could call it a degree 1 polynomial, but usually in this class, we would call this one a linear function. So this function is linear. Now thinking in terms of geometrically, anyone happen to know what the slope should then be if that's a linear function? Yeah, good question, or good call, folks. And sorry, the question was, if we were trying, oh, hang on, that's distraction. That might be a bit of confusion there. If the function is g of x, the question should have been, what is the derivative g prime of x? Thinking geometrically about the function, the fact that it's linear. And as Keenan said, it's exactly the 7/3 there. That's the slope of the line itself. Let's explain this a little bit better and fuller using graphs. But that's the whole punchline to this one. If we happen to know that we're dealing with a linear function, the derivative is completely done. It's just the slope itself. That's kind of cool in a sense. And here's how we've come together thinking in terms of those graphs, just like we've been producing all along. If we had to plot this function, it's actually kind of annoying. I have to go down 9 units. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we are, -9. They have to go up 3, up 7, and then right 3. So 1, 2, 3, 4, 5, 6, 7. That looks right, down 2, right 3. Okay, so here's my quick sketch using the slope-intercept format of the line. That last piece doesn't look right. Slightly better. But you know, part B is not any different than part A. The only difference is this one had slope 0, this one has slope 7/3. If you pick any point on this graph, say it's here, and you want to know the slope of the tangent line, that's not too hard because the tangent line completely overlaps the original line itself. So the slope of the tangent line is automatically 7/3, which means the derivative is automatically 7/3. And if we, just for the sake of parallelism, were to sketch the derivative down below, let's see, that's 2 1/3. Here's the sketch of the derivative itself. And this is y equals g prime of x. So the takeaway so far, if we zoom out just a little bit more, is if you have a constant curve, the slope is always zero. Take the derivative and your derivative collapses to another horizontal line right on the x-axis. If it's any other linear function whatsoever, the derivative is the slope and it becomes a new constant function at height equal to that slope. But here's the other big takeaway. The derivative of a constant is zero, and the derivative of a linear function is just its slope itself. Now, if we keep going up higher and higher degrees, that's where we need the next section, 3.3. Well, let's make that our next question. This will be the last one for the notes. Any last questions at all, folks, with the big takeaway in these notes? The derivative being the slope of the tangent line? Okay. Well, here's the last one for this section notes. This section's notes is kind of short because, again, we're really kind of using it as just a couple more additional topics from 3.1, where we did a lot of the harder work. So we will calculate one more time a derivative. We're going to use it with by using the definition of the derivative, the limit definition above. And this is the one where it's not quite as easy because it's a degree 2 quadratic function. But there's still some hints. That's a constant term, so that should just vanish. The derivative of a constant should be 0. That's a linear term. That means when we do a derivative, a -5 should pop out. And that's the hard term. That's going to require us to do this from scratch before we see some of the formulas in the very next section. So think of this as just one more practice problem. Essentially, this is a section 3.1 problem, where the only difference is we're inputting in the variable x rather than a. So to compute this derivative, first piece we need is f at x plus h. Well, let me start just by recopying it down so I have something to color code and look at a little bit closer. The derivative of f at x is equal to the limit as h goes to 0, f at x plus h minus f of x. If you did this problem, say, on exam 2 or the final exam, I'll say this part right here to alert you it's through this definition. But I don't care if you put in an a or an x. You're going to be doing the same problem either way. So let's divide this up. Do the f at x plus h first. That's a significant amount of algebra just on its own. F at x, let me fix that typo there, x plus h. Places x plus h here, so it's 3. Power 2 minus 5 times. X plus h goes here as well, so I'll just blow up a parenthesis for both of those. And then drop in x plus h. Then we have to expand this and FOIL it. So the thing we put down in the notes is that's just x plus h times x plus h as scratch work. When you FOIL that, you get x squared plus xh plus hx plus h squared. The middle terms do combine as like terms, so altogether this is just 3 times x squared plus 2 xh plus h squared minus 5 times x plus h plus 1. So it's progress, we're getting there. I'll do the distributions and then we're done with this part. 3x squared plus 6 xh plus 3h squared. Another round of distributions, minus 5x minus 5h plus 1. And notice there are no like terms whatsoever on this to combine and cancel with. That's okay, because we're going to get some like terms from the negative f of x part. Let's let that be our new chunk, including that negative sign. So negative f of x is negative of this thing, 3x squared minus 5x plus 1. So that means it's going to be equal to negative 3x squared plus 5x minus 1. Now we can put all of it together back up here and finalize the limit. Actually, we're most of the way through this problem. We now have derivative of f at x is limit h goes to 0. Here's where we put in a kind of a gigantic fraction bar. It's kind of overwhelming at first, but just think in terms of the chunks, the components, as we drop these in. Naomi sees, I think there was a mistake in the last blue. It's supposed to be negative 5x minus 5h. Oh yeah, thanks for spotting that. That's a weird typo there. I put in, that would have combined to negative 10. So negative 5x on this spot here. Let me highlight that error. Thanks for spotting that, Naomi. Good eye on that mistake there. You know, once one mistake is spotted, I start to get suspicious. Let me double check the rest of the work. Okay. Other questions so far? Or comments? Okay. And good eye with that mistake, because one thing you'll notice is if I let that mistake hold and I just copy that into the problem, I'll have a negative 10h. There is no way this limit's going to work out. It's going to be broken because it won't cancel with that one, the positive 5x. And why is that so bad? It means we will never divide out that h cleanly, and so we can never use direct substitution with continuity. The name of the whole game is to cancel that h some way, somehow. So now with that term corrected, we're in business. Let's drop in this component. 3x squared plus 6, xh plus 3h squared minus 5x minus 5h plus 1. Now I'm substituting all this in with the sign, so we can just copy that in directly. Negative 3x squared plus 5x minus 1. Now we have a really fast check. Everything without factor h should cancel. That's working out. 3x squared is gone. We have a 6xh, nothing to do with that, but it's okay. It has a factor h with it. 3h squared. Here's the next thing that has to go. Negative 5x, positive 5x will cancel. Then down the line, positive 1 has to cancel as well. But we do have its opposite on the far right. Everything remaining involves a factor h, so we'll actually just factor it out. F prime of x is now the limit as h goes to 0 of, here's the h factored out, leaving behind 6x plus 3h minus 5, all divide by h. And that's the satisfying clean cancellation we want to make right at this step. Once we made that cancellation, this is now continuous at h equals 0. And that deserves an exclamation mark. We're not saying 0 factorial, just we're excited because we have a continuity at h equals 0. So we take this value, that's the whole punchline to continuity, directly substitute in a 0 for that h. And we have that finally, f prime of f at x gives us a 6x minus 5. But notice what happened. The constant term is gone because the derivative of a constant should be a 0. That's a linear term with slope negative 5. And we have exactly a negative 5 here. The thing that went different was the degree 2 term, but something else happened. This power 2 came down, multiplied the 3 to give us a 6. And the exponent, which was a 2, has dropped to a 1. It turns out that is no coincidence. That happens for every single power function, like 3x squared, 12x to the power 7, and so on. That is always going to work, whether we run it through the limit or just use the formulas in the very next section. But this is pretty much the review of what we did in 3.1, focusing on just the x itself rather than putting in a value a. This 6x minus 5 is now the slope of the tangent line to the original curve at any value input x. Any last questions at all, folks? Finally getting through this one. Okay, it is a lot of work. It's a lot of careful algebra as well. Again, the smallest of mistakes, and we're suddenly just stuck on the limit. That finally answers the question of why do we care about limits so much? What is continuity doing for us? essentially completing our last step on computing the limit. But the bigger takeaway in these notes is, how does the function here relate to the derivative down below? Let's take one last look into that to think about that concept, really the harder concept of this section. And then we'll see how to do these derivatives a lot more efficiently and cleanly in the next section. So I want to put down two functions. The original one, f of x equals 3x squared minus 5x plus 1. I don't think I could put in an f prime no matter how hard I try, so I can't plug it in like that. Or yeah, I can. I didn't realize that works. You could just put in an f prime and it plots it. That's kind of amazing. I might have to save that for later. What I was going to plot was y equals 6x minus 5, but that's the same plot. I'm gonna remember that one for later, so now it's black this time. But it's the same curve as this one, 6x minus 5. We can tell because the y-intercept is right at -5, and the slope being 6 means you move up 1, 2, 1, 2, 3, 4, 5, 6, right 1, and you're back on the graph. That looks accurate. Yeah, I agree. I've learned more and more about Desmos the more I use this. In fact, I never knew about Desmos except I was just trying to plot something in class, and a student suggested it, try Desmos, and I've been using it ever since. That was like 6 years ago or something. There's a lot of crazy stuff you can do in Desmos. But let's take a look at this curve. The original curve is the one in green. Oh, that's awesome. Yeah. The original curve is the one in green that we see through here. And notice that it bottoms out right at that spot. Well, that matches with what we have right above. This is where the derivative goes to 0. The curve is decreasing as we move all the way to that horizontal tangent line. That's why the derivative in black is always below the x-axis. The derivative is negative until it gets to this spot. That matches up with the horizontal tangent line. Then the graph goes positive. It's increasing faster and faster and faster. That's why the derivative in black converts to positive. The slope is getting higher and higher. And that's why it's moving up and up. So every point on here, if we look into the slope of the tangent line, here it's negative, and the specific negative value is just the y-axis point on that graph below, the original derivative. Well, that's derivatives in a nutshell, and we'll be returning to the geometric nature, practical interpretations, and context with implied problems in the next sections. But any last closing thoughts or comments, folks, before we go to 3.3? Okay, 3.3 is now going to collect together one nice spot, a lot, not all, but a lot of the tools that allows us to sidestep this big step. The interpretation of the derivative is the same, but now we're going to look into how to calculate it faster and faster, because if we have to resort to the limit definition on every problem, we won't get too far in this course. It would be a lot of work. It'd probably have to be a 2-semester course, really. Our derivative formulas in this textbook are primarily stated in Leibniz notation. So this is what the formulas are going to look like in section 3.3. We're going to go down the line to see how these pieces connect, starting with the derivative of the constant, the power rule, constant multiple rule, and so on. Then our major goal is, once we collect all these tools, to see how to differentiate these functions as efficiently as possible without having to resort to the limit definition. And for the application problem, we'll be finding the derivative of the length of a particular Alaskan rockfish, that looks like it is, computing a derivative like this, and giving another practical interpretation for its value. So these notes start off by just kind of a rule by rule. There's a lot of white space here because it's not sufficient to say if c is a constant, then the derivative is 0. We should look into a lot of examples. So here's a lot of ways that this derivative of constant formula can come into play. If you have a function f of x equals, let's let it be, say, 13 square root 13. It's now a constant function because x is nowhere whatsoever on the right-hand side. And this formula, again, it's stated in Leibniz notation, but you could just simply say f prime of x is 0, and that's the whole essence of this rule. The derivative of constant is always 0. If it was a different problem, say y equals, maybe this one is 2 to the power 3. That's just a fancy way to write 8. But it could be more abstract looking, like 2 to the power 3.1. You can put a number down to that as well. It just looks like lots are going on when you say 2 to the power 3.1. But this is all it is. 2 power 3.1. It's approximately that number right there. It's still constant. And so if you use this differentiation formula, you can either write y prime or write dy dx is 0. Either way, that's the whole essence of the rule. But it is tricky because, like we discussed before, the constants can sometimes be well disguised. So the big takeaway is a function is constant if there is no variable in its definition. Naomi says, will these rules be given to us on exams or will we memorize them? Yeah, for his purpose of exams, I'm going to do a roundup, just like we did on exam 1. There's a formula sheet at the end. And I'll be doing the same thing with our upcoming exam. I'm going to do a roundup of all these rules as part of the last sheet on the notes for our upcoming exam 2. And Haley says, in quizzes or exams, does it matter if we write it in a certain way? I would say absolutely not. It's important to see it both ways because sometimes problems come at us in this format or sometimes in this format. But if you rewrote this as just y prime or dy dx, I'm completely fine with either notation. It's always going to be up to you. Other questions so far? Okay, the next most amazing rule beyond the constant function rule is the power rule. The reason it's called a power rule is because y equals, say, x to the power 7, for a specific example, is a power function. Because it's just a variable raised to some specific power. And the power rule we will use a lot, and we're also going to have to reverse these rules as well. So we'll see it in its reverse format. It says if you take the derivative of x power of n, say it's x power 7 or x squared, like in the last problem, the power comes down and the new exponent is 1 less. It always drops by 1. So that's a fantastic definition or fantastic formula, because doing this limit through the definition is going to be a lot of work. You can imagine you have to expand out x plus h to power 7, lots and lots of stuff you'd have to do there. But if you use that power rule, you could call this y prime equals, let's run through the rule. The essence is the power that's here moves down and multiplies. So it's going to be 7 times x to the power of, always 1 less. So now it's just power 6. And you don't have to put that multiplication there. That's just there for emphasis. Any questions at all, folks, with our first official use of the power rule? Okay, and I wish I didn't close that. Let's just pull this up really quick while we're thinking about the power rule. If we think about what happened here, that was the power rule. This was x to power 1. So if you differentiate, say, just x itself, it turns into a 1. Let's put that on paper. If the function is f of x equals just x, that is still a power rule problem. It's just that the power isn't displayed explicitly. You could rewrite it, though, as f of x equals x power 1. Then the derivative would be f prime of x 1 comes down right here and multiplies. So here's 1 times. The new power of x is 1 less. So it would be 1 minus 1 for a power 0. And it looks really funny, but we'll say x power 0 is 1 in this context. And so f prime of x would equal just 1 altogether. And that's pretty much what happened with this x. It became a 1, and all we saved was the -5 when we got that in their output. And when we differentiated the 3x squared, we just got a 6x to the power 1, no different than what we did going from here to here. So that's the power rule so far. It has one particular case where it can get kind of tricky, which sort of explains why I have exponent laws just under the section 3.3 notes. But any questions or comments with those two quick examples so far? Okay, here's a really tricky example. Let's suppose it's a function h of x, h because this is kind of a harder problem unless we see the trick. And h of x is 1 over, let's let it be, say, 5th root of x squared. We want to differentiate that function. We have to do a little bit of algebra on it. So exponential notation is going to be a requirement on this one. Let me actually kind of break this apart with some borders, just because I seem to have examples everywhere now. So here's one example and a weird border. Here's a different example with an exponent law above. And here's the new tricky example. We're still using the power rule, but it's surprising that it works here. The first big concept is the nth root of a base a is a to the power of 1 over n. So we have to use that concept. And the next concept is a to a power of, let's say, m raised to a power of n is a to the power m times n. And another concept we need is 1 over a to a power of a negative, actually, let's write it more like what we see on this notes. A to a power of a positive exponent n is a to a power of a negative exponent in that way. And if it was different, if the exponent was negative, a to the power negative n in the denominator would be a power positive n in the numerator. This last exponent law is essentially saying we change positions from numerator to denominator, we change the sign of the exponent. In this configuration, exponents multiply, and the nth root is just a fractional exponent, 1 over n. We put all that together, we can redefine h of x in a format where the power rule is just much, much easier to apply. First thing we do is we unpack the radical notation, the 5th root. Write this as 1 over x power 2 to the power of 1/5. So that was the first exponent law. Now we use the second exponent law. The m power and the n power multiply, and it doesn't matter if one is a fraction and the other isn't, or they're both fractions, or they're both irrational numbers, that power rule here still holds. So then it becomes 1 over, actually let me kind of drop a line, becomes 1 over x to the power of 2/5. Then we still don't want to use a power rule in this format, because a major thing about the power rule is you don't have the base in the denominator, it's in a numerator instead. So we get more space for this one. We move that up into a numerator, so now h of x is x to the power negative 2/5. So that's this power rule here. But finally, after doing all that work, we can say the exponent n is negative 2/5. N could be any real number whatsoever, an irrational number, a fraction, it doesn't matter. This power rule is going to work the same. N is going to move down to the front as a coefficient when we take the derivative, h prime of x. So now here's the negative 2/5. And the new power of x will be 1 less. That's the n minus 1 part we see up here. So if we take negative 2/5 minus 1, that's subtracting 5/5. We'll get a negative 7/5. and it will go up here as a -7/5. So this is like the worst case scenario for the power rule. This one here in, I forgot what color this is, violet, I think. If you have weird things going on, you have to unpack it, get to the exponent, bring the base up to the numerator, but finally, this is where the power rule takes effect. And the big takeaway of doing a kind of a hard problem like this one is, no matter how bad your exponent looks, it always moves in front as a coefficient multiplying, subtract 1, and you have your new exponent. Whether they're positive or negatives, this rule always works exactly the same for any real number n whatsoever. Well, because the power rule we use probably the most in this entire class, here's 3 big examples in boxes and in this color right here. Any questions or comments at all, folks, on getting through either one of these examples? Okay, now the next rule is the so-called constant multiple rule. Here's where it's not as bad or as abstract as we've seen so far. Here's where we're going to start putting ideas together, like say, for example, to get the derivative of that -5x right there to come out as a -5, that's actually the power rule and the constant multiple rule, both at the same exact time. And same with that 3x squared. Let's bring both of them down just for the sake of emphasis. The constant multiple rule says if you take the derivative of constant times a function, nothing happens to the constant. It just multiplies the derivative of the function. So that's a fantastic rule as well. Here's what it would look like in typical problems, whether it's in Leibniz notation or Newton's prime notation. Let's first do a Leibniz notation rule. We have y equals -5x. Then to differentiate this, let's call it to dy dx, we'll get -5 times just the derivative of x. That's what's being emphasized here. The f of x here and here is playing the role of the x in this current problem. So here it is, differentiate x. Let me highlight it slightly differently. And differentiating x, that's just a power rule. Let's do this one on the margin to the right. The derivative of x, if we write it as a prime notation, is really just the derivative of x power 1. And that would be 1 times x power 0, or we'll just say 1 as a shorthand. Or you can think it even differently. It's still just a linear function, whether you call it x or 7/3 x minus 9. The slope of x itself is just a 1, much like the slope here is 7/3, and we pick up the 7/3. So altogether, dy dx for the constant multiple rule is just -5 times 1, so just a -5 altogether. Or again, thinking geometrically, that's a linear function with slope -5, so we pull down the -5 there. So that's one version of the constant multiple rule. Any questions with it so far? A different version could look like this. Let's suppose the function is f of x, and it happens to be, say, a 3x squared, kind of motivated by the last problem we solved in 3.1. The constant here is 3, multiplying the x squared. If you were to differentiate this, you'd say f prime of x is going to be equal to, first, the constant multiple rule says nothing happens to that 3, stays put exactly where it is, because it's multiplying a function that varies with x. Then you do the power rule in this part. The derivative of x squared would produce a 2 times x to the power 1. So this is through power rule on that spot. And we're pretty much done at this point. You would get that f prime of x is just 6x altogether in its most simplified form. But what's the shorthand here? 2 multiplied to 3 because it was in front, a constant multiple rule. This is just saying you're allowed to do that. So 2 multiplies it, we got a 6, and the power is 1 less. Now a power 1, written this way in its most simplified form. Constant multiple rule is just saying you're allowed to do that. We didn't cheat. This is a bona fide process. And this is how we're going to see it most often. We'll just go from here to here on that derivative. So far, we've looked at all the rules that's going to allow us to take the derivative of this function right here, but there's still one last thing missing. What about the pluses and minuses? We have another rule that goes along with that as well. That's going to be the sum rule and the difference rule. So it tells us if you're adding functions together or subtracting them, you can differentiate them term by term by term. That's a fantastic rule because it allows us to kind of just divide and conquer, differentiate one term at a time. Differentiate that one, we get 6x. Differentiate that one, it's just a -5. That one's a constant, so that term will go to 0, and that's the full justification without looking at the limit, how we get 6x minus 5. So we're nearly through the long list of rules that we see so far. Let's put down a couple examples just for this one. If y was something like, say, -7, x squared plus 12x minus 92, it looks like a really imposing function altogether, right? But if we're going to differentiate it, whether you called it y prime, kind of want to make it look like an angle, not power 1, or you called it dy dx, the sum rule and the difference rule says, just look at one piece at a time. Don't look at the whole forest, just look at the individual trees, in other words. The constant multiple rule says that -7 that's multiplying stays in place. The power rule says 2 is just going to come down and multiply. So here's all of our rules interacting all at the same time. Multiply here, we get -14, x to power 1. So we'll just write it as a 1. Power drops by 1. Here, the power that we see is really just a 1. So 1 multiplying doesn't change that. We just go plus 12. The new power is 0, so x just vanishes. Or it's a great thought to think in terms of that's a linear function with slope 12, so you just get 12 as a result. Or a third way to think about it is if x is to power 1, it vanishes and you just keep the coefficient. Last, we're still using the sum and difference rule, so we move over, do this one separately. That one's a constant. Now notice this is different than the constant multiplying. The constant multiple rule says that -7 stays in place, it just gets multiplied by 2. But if there is constant all alone, that's a true constant function, it goes to 0. So that would be a plus 0. And often we wouldn't even write that down. We would just simplify down to -14x plus 12. So y prime is -14x plus 12 altogether. And that's our last rundown for the rule. Again, it's cool to see how it happened on this one. So let me see if I can zoom out just a touch. Because we worked really hard on this, right? But the rules altogether are just telling us that if you differentiate this function, you get a 6x on that term, a -5 on that term, and the constant function goes to 0, so we never wrote it in. And it doesn't matter how complicated that gets, how imposing the coefficients or the powers are, same exact process applies. Well, does that make sense to folks so far, getting down to this value here? Okay, we're going to practice these more and more when we come back a little bit more refreshed on Thursday. But there's one last rule I need to tell you about, the one that's the nicest and yet the trickiest all in one. This function is weird, e power of x. And e is weird too. E is approximately 2.71, and this is called Euler's number. Euler was a massively, gargantuanly prolific mathematician. Everyone kind of bonds over people like Isaac Newton and even Leibniz because they discovered something amazing. But Euler published so many mathematical results that if I was to say, go from end to end of this room and just put all of his manuscripts together, that's not the sum total of his research. He put out a lot. He continued to put out mathematical work even after he went blind. He just had his assistants notate for him after he was losing his eyesight. So his number is this, E 2.71. And this function, being an exponential function, is bizarre. The derivative is itself. When you think about that and you write f of x equals e power of x, that's an exponential function. F prime of x, notice how it overlaps itself completely. That's just this function action. Every spot on this curve, the y-coordinate is the slope of the tangent line at every single spot. An extremely bizarre function in a certain sense. But it's an amazing formula. It says y equals e to the x. Our work is done. The derivative is e to the x. And this doesn't work with every exponential function, so we need more rules as we go into the next sections. But there's not a lot to say about that. Maybe a different kind of question could be y equals 10 e to the x. Then y prime would be 10 e to the x, and it's done right at that step. And maybe one last thought. If y equals, maybe it's 10 x squared minus 10 e to the x. Here's where it gets a little bit more confusing. This one's a power function because the base is x. This one's a base e exponential function because x is in the exponent position. So if you differentiate this function, let's give Leibniz notation a little bit of love and call it dy dx. We would get 2 multiplying the 10, so 20, x power 1, so just x. But this x does not come down and multiply. It stays exactly where it is. The derivative of the last term is just negative 10 e to the x. And it just stops right there. We'll be expanding on this rule. You might wonder, what is the derivative of 3 to the power of x? We'll see how that one goes later on in the notes. But so far, this is the full rundown of all the formulas we're going to be using in section 3.3. Our next goal is to revisit some concepts like slopes of tangent lines. We'll show how to do this one really fast now. We'll show how to do higher order derivatives like the third derivative, how to work through applied problems, and then we'll just do a massive review of all the rules and see how they interact together on this long list of problems down below. So that's going to be our major work when we come back. A little bit more fresh on Thursday. Review all of these formulas. Harry Brazier says, don't look at the whole forest, just look at the individual trees. That's an amazing motivational quote. Thanks, I agree as well. And that's kind of a good thought for mathematics as well. No matter how ugly this gets, just look at each component, divide or conquer, or look at the individual trees instead of the whole forest is a great way to think about these. Well, any other last questions or comments so far, folks, before we call it a night? Okay, so it was a lot of formulas to end class today, so thanks for your patience on getting through them. We'll definitely review them, and these are the kind of things that we will see on the last page of exam 2 and a final exam as well when we're taking exams. But once we practice these a lot, probably they're going to become secondhand nature, just kind of like exponent laws as well. But have a great night, folks. We'll be back to it on Thursday. Thanks, folks. Thanks, you too.